Have you ever stopped and wondered how an AI can just create a picture of a cat that has never, ever existed? It's kind of mind-blowing, right? Well, the secret sauce isn't magic, it's math. Specifically, it's about measuring the difference between the AI's best guess and the real deal. In this explainer, we're going to peel back the layers on some super powerful tools that make this all happen. All right, so here's our game plan. First, we're going to really nail down what this measurement problem is all about. Then, we'll take a tour through 3 amazing mathematical tools, KL divergence, JS divergence, and the Wasserstein distance, looking at what makes each one tick. And to wrap it all up, we'll see why picking the right tool is absolutely crucial for building the kind of AI we see today.
Okay, let's start at square one. Before we can get an AI to learn anything, especially something creative like making art, we have to figure out a really fundamental challenge it's up against.
Seriously, think about it. You can't just pat the computer on the head and say, good try. We need a concrete number, a score, that tells the AI exactly how close it's getting. And we're not just comparing one fake photo to one real one. Oh no, we're comparing the AI's entire universe of possible cat photos to a giant database of all the real cats out there. In AI speak, we call these collections of data distributions. So let's bring in our first tool for the job. This one's a real classic, straight from the world of information theory. It's called Kullback-Leibler divergence, but everyone just calls it KL divergence for short. Let's stick with our cats. Imagine you have a perfect, godlike knowledge of every cat photo on the internet. That's our true reality, which we'll call distribution P. Now imagine our AI is trying to describe those photos with its own, much simpler model. We'll call that distribution Q. KL divergence measures how much surprise you'd feel if you are forced to use the AI's simple model to find cats. If you're constantly surprised, whoa, I didn't expect that, the KL value is high, and that tells us our AI has a lot of learning to do. Okay, don't let the math scare you. Let's break it down. P of X is just the chance of seeing a certain cat, say a ginger tabby, in our real-world dataset. Q of X is the probability our AI assigns to that same ginger tabby. This formula basically averages out the surprise across all the different kinds of cats. As our AI keeps getting the probabilities way off, that surprise score is going to shoot way up. Now here's where it gets a little weird, but really, really cool. KL divergence isn't like distance in our everyday life. You know, the distance from your house to the store is the same as the store back to your house. Not with KL divergence. The distance from P to Q is totally different from the distance from Q to P. It's what we call asymmetrical, and it fundamentally changes how we train our AI. And this visual really drives that point home. Let's say our real-world data has 2 big groups of cats, big fluffy orange ones and sleek black ones. Forward KL will try its best to make a model that can generate both, even if it means the results are a little generic or blurry. It's an overachiever trying to cover all the bases. Reverse KL, on the other hand, is a perfectionist. It might look at the data and say, you know what? I'm just going to get amazing at making black cats and just ignore the orange ones. It aims for sharp, perfect images, even if it has to sacrifice variety to do it. So this brings us to a huge problem with KL divergence, especially when an AI is just starting out. It's totally normal for a brand new model to create some weird stuff that looks nothing like a cat. If we look back at our formula, you'll see that Q of X, the probability from our AI model, is sitting right there in the denominator of a fraction. And as anyone who's taken a math class knows, that can spell trouble. Right, so what happens if our real dataset has a cat wearing a little hat, but our AI has never even dreamed of a cat in a hat? The AI says the probability of that is 0, and suddenly we're trying to divide by 0. And in math, that's the one thing you just can't do. The result is infinity. The AI's error score just explodes. And when that happens, the model has absolutely no idea how to fix itself. The training process just breaks. It comes to a grinding, screeching halt. So, how do we fix this catastrophic failure? Well, let's look at the next step in the evolution of this idea. We've got a clever fix for this called Jensen-Shannon divergence, or just JS divergence. JS divergence is pretty slick because it tackles the 2 biggest headaches of KL divergence head-on. First, it's symmetrical, so the distance from P to Q is now the same as from Q to P. And second, it has a really neat trick up its sleeve to dodge that whole dividing by 0 nightmare. So here's the trick. Instead of comparing P and Q directly, JS divergence creates a new middle ground distribution called M. It's literally just the average of the other 2. Then it measures the KL divergence from P to this middle point and from Q to this middle point and averages them out. Because M is an average, it guarantees there's always some probability, so we never have to divide by 0. It's a simple but totally brilliant workaround.
Now, JS divergence was a massive leap forward. It was actually the engine behind the very first Generative Adversarial Networks, or GANs. But it has its own Achilles heel. If our AI's images and the real images are completely, totally different with 0 overlap, the JS divergence score gets stuck at a single constant number. And the problem with a constant number is that its slope, or its gradient, is 0. This means the AI gets no signal, no hint about which direction to go to get better. It's like being lost on a perfectly flat, featureless plane. You can walk for miles, but you have no idea if you're getting any closer to your destination. The learning just stops.
To solve this vanishing gradient problem, we have to fundamentally shift our perspective. We need a totally new way of thinking about distance. And that brings us to a very powerful metric called the Wasserstein distance. Instead of thinking about abstract ideas like information or surprise, Wasserstein asks a much more physical, intuitive question. It asks, how much actual work would it take to turn one pile of data into another?
And the best way to picture this is with a fantastic analogy: the Earth mover's distance. Imagine your AI's generated images are a big pile of sand, and the real-world images are a hole in the ground you need to fill. The Wasserstein distance is just the minimum amount of energy or work it would take to move all that sand to perfectly fill that hole. It's such a practical, real-world way to think about the difference between two things.
And the beauty of this is that even if your pile of sand and your hole are on opposite sides of a field, even if they don't overlap at all, there's still a clear, meaningful amount of work that needs to be done. This gives our AI a constant, super useful signal it can follow to get better and better, even when it's starting from way off. It completely solves that nasty vanishing gradient problem. Okay, let's put it all together now. We've seen 3 very different ways to measure the distance between data, each with its own pros and cons. So why does this all matter when we're actually building stuff?
This table is a fantastic summary of our journey. KL divergence is powerful, but it's brittle. It explodes if the data is too different. JS divergence fixes the explosion problem, but can just stop, leaving the AI with no way to learn. And then there's Wasserstein, which gives us a smooth, meaningful distance no matter what. It just works.
And right here is where you see the real-world results of all this theory. Early models called VAEs often use reverse KL, and that's partly why their images could be a little fuzzy. The first GANs used JS divergence, which was a revolution for image sharpness, but they were notoriously difficult to train. And then came WGANs, Wasserstein GANs. They used the Earth mover's distance, and the result was much more stable training and images that were and still are stunningly realistic. You know, this whole progression from infinity problems and vanishing gradients to the beautiful simplicity of moving dirt, it's just an amazing story of creativity in AI research. And it really leaves us with a fascinating question to chew on. As AI gets even more powerful and complex, what new kinds of math, what new kinds of distance metrics are we going to have to invent next? And what incredible new things will they allow AI to do?